Imagine a world without soap. No fragrant bubbles, no squeaky clean hands, and certainly no rubber duckies enjoying a foamy bath. Soap is a cornerstone of modern hygiene, yet its origins and chemistry are as rich and layered as a triple milled bar. Let's dive into the bubbly world of soap, exploring its history, chemistry, and the science that keeps us clean. A brief history of soap, from ancient suds to modern bubbles. Soap's history is as old as civilization itself, dating back to 2800 BC when the Babylonians pioneered soap making. They created soap-like substances by boiling fats with ashes, a rudimentary process that laid the foundation for what we now consider essential for cleanliness. By 1550 BC, the Egyptians refined this technique, incorporating a mixture of animal fats, vegetable oils, and alkaline salts. This innovation not only kept them clean, but also treated skin conditions, showcasing early medicinal applications of soap. The Roman Empire further elevated soap's status. By 100 AD, they adopted and expanded its use, with public baths becoming central to Roman social life. Moving into the medieval period, soap making evolved in the Middle East. Cities like Aleppo and Nablus became renowned for their high-quality soaps, especially olive oil-based varieties. By the 13th century, soap making was not just a craft, but an industry with carefully guarded recipes. When soap makers arrived in North America by the 1600s, they brought with them centuries of expertise. These developments set the stage for soap's transformation into an industrial commodity in the 19th century. The chemistry of soap, breaking down the basics. At its core, soap is simple yet elegant chemistry. Fundamentally, soap is a salt formed by the reaction of fatty acids with an alkali. This process, called saponification, is the foundation of soap making. It starts with triglycerides, which are fats or oils composed of glycerol and 3 fatty acid chains. When mixed with a strong base, typically sodium hydroxide, lye, the triglycerides break apart into glycerol, used as a moisturizer, and soap. The fatty acids used determine the type of soap produced. For instance, coconut oil creates a hard soap with a strong lather, while olive oil yields a gentler, creamier soap. The sodium or potassium salt of these fatty acids is what gives soap its cleaning power. The hydrophilic, water-attracting head of the soap molecule bonds with water, while the hydrophobic, water-repelling tail binds to oils and grease. This duality allows soap to act as a bridge, lifting dirt and grime from surfaces and making them Saponification, the heart of soap making. Saponification is where the magic happens in soap production. This chemical reaction occurs when triglycerides, the building blocks of fats and oils, interact with a strong alkali, typically sodium hydroxide, lye. The reaction breaks the triglycerides into their 2 components, glycerol and fatty acid salts. The fatty acid salts are the soap, while glycerol often remains as a moisturizing agent. Take, for example, stearin, a fat commonly found in animal tallow. When saponified, stearin reacts with sodium hydroxide to produce sodium stearate, one of the most common ingredients in commercial soaps. The process generates heat, which can be controlled to produce different textures of soap, from smooth and creamy to firm and long-lasting bars. Historically, lye was obtained from wood ash, which was labor-intensive and imprecise. Today, the use of refined sodium hydroxide ensures consistent results. The process can be tailored further by adjusting the oils used, allowing modern soap makers to create specialized soaps for different skin types and cleaning purposes. This reaction remains soap molecules, the dynamic duo of hydrophilic and hydrophobic. Soap molecules are nature's tiny multitaskers, showcasing their unique amphiphilic properties. This means they possess 2 distinct ends, a hydrophilic head, which is water-attracting, and a hydrophobic tail, which repels water but is attracted to oils and grease. The hydrophilic head is typically made up of a carboxylate group, while the hydrophobic tail consists of long hydrocarbon chains. This dual personality allows soap to perform its magic by bridging 2 worlds that normally wouldn't mix, water and oil. When you use soap, the hydrophobic tails latch onto oil, grease, and dirt, while the hydrophilic heads stay immersed in water. This interaction breaks down the surface tension of water, making it easier for the soap to spread and penetrate surfaces. The ability of soap to emulsify oils, turning them into smaller droplets that can mix with water, makes it indispensable in cleaning everything from greasy dishes to your skin. Without these amphiphilic properties, soap would... How soap cleans? The micelle mechanism. When soap is added to water, its molecules self-assemble into tiny structures called micelles. These micelles are spherical clusters where the hydrophobic tails congregate inward, avoiding water, while the hydrophilic heads form the outer layer, happily interacting with water molecules. This configuration is crucial for soap's cleaning action. Micelles act like microscopic traps, encasing oil and dirt within their hydrophobic core. As you rub soap onto a dirty surface, these micelles surround and capture greasy substances, breaking them down into smaller water-soluble particles. This allows the dirt to be easily rinsed away with water. Think of micelles as little scavengers, tirelessly hunting for grime and ensuring it doesn't stick around. This mechanism is not just essential for cleaning hands or laundry, it's the same principle used in creating micellar water. Hard water versus soft water, soap's arch nemesis. Hard water is soap's natural nemesis, and understanding why involves a bit of chemistry. Hard water contains high levels of dissolved calcium and magnesium ions. These ions react with the fatty acid salts in soap, forming insoluble compounds often referred to as soap scum. This residue not only reduces the soap's ability to lather, but can also leave unsightly deposits on surfaces. Soft water, in contrast, contains fewer of these ions, allowing soap to perform at its best. When soap is used in soft water, it produces a rich lather and effectively removes dirt without interference. The difference between the two types of water is why people in areas with hard water often rely on water softeners or switch to detergents, which are more resistant to hard water's effects. This battle between hard water and soap is not just about inconvenience, it has significant implications for industrial cleaning, plumbing maintenance, and even personal hygiene. Modern soap making. From artisanal bars to industrial giants. Soap making has come a long way from boiling fats over open fires. Today, it spans from small-scale artisanal practices to massive industrial operations. Traditional methods, such as cold and hot processes, remain popular among small soap makers. In the cold process, fats and oils are mixed with lye and left to cure over several weeks, creating soap bars rich in natural glycerin. The hot process speeds things up by cooking the mixture, resulting in a ready-to-use product within days. On the industrial side, continuous processes dominate. These involve a more streamlined approach, where fats and oils are chemically treated, purified, and blended with additives like fragrances, colorants, and moisturizers. Modern soap making also includes the production of synthetic detergents, which are not true soaps but share similar cleaning properties. Despite the diversity in techniques, saponification remains at the heart of soap production, a timeless process that bridges artisanal craftsmanship and industrial efficiency. This evolution reflects soap's enduring importance in both personal care and global commerce. Beyond cleaning, soap's role in health and society. Soap transcends its role as a cleaning agent, serving as a cornerstone of public health and an integral part of society. Regular hand washing with soap is one of the simplest and most effective ways to prevent the spread of diseases, including respiratory and gastrointestinal infection. Thanks for watching. And that's the story of soap, its history, chemistry, and impact on our lives. If you enjoyed this dive into the sudsy world of cleanliness, make sure to give this video a thumbs up and share it with your friends who might want to know why soap works so well. Don't forget to subscribe to our channel for more future videos. Stay curious, stay clean, and see you in the next video.